Good afternoon everyone, I am Mr. Ish. Thank you for joining me for this video. In this video we're not looking at material which is explicitly new. I am reframing material which you might have seen in a variety of other videos, clumping them all into this one with regards to limit properties of the natural log and the exponential function. You know both the natural log and the exponential equations are functions. They're functions because they satisfy all aspects of what a function is, the definition of that function. We don't need to revisit what the definition is because you would know that. But with regards to these functions, if you look within the same plot, a exponential function which would go in this manner right here to 0, 1, and then you look at the natural log function. These are functions which are not translated or transformed in any way. You have this, it would go right here through 1, 0. Here's my exponential. When you look at both of these, in terms of their individual curves, they pass the vertical line test very easily. Individually, there's no point through which a vertical line will cross that curve at more than one point. It's only at one point that a vertical line crosses, and there's always, for any given point that you select in terms of the domain with regards to the range, or you can say an x value put into either of these curves with regard to the generated y value, the output, there's always a one-to-one correspondence for either of these functions, a one-to-one correspondence. There is no situation here where you would have this arise where a single x value will generate two types or more y values. In all instances, you have a single x value correspond clearly to a y value, and these are very well established functions. An interesting point about the exponential function with regards to the domain, we know the domain is the set of inputs for a given function or an equation such that when you plug in those inputs, corresponding x values, you will get a satisfied number of outputs which are your y values. For the exponential function, you know the domain is always minus infinity to infinity, and that's exactly how it is. The range with regards to the exponential function is going to be from 0 up to infinity. Why is this the case? Because here you have your x-axis, y equals 0, and the exponential curve, the unadulterated exponential curve, will not go below that. With regards to the natural log function, the domain over here, you can see clearly the domain is the extent, the lateral extent of a function or a curve or an equation along an x-axis dimension. Here you can see it's 0 up to infinity, not including 0, because with the natural log you have this x equals 0 line to deal with, because you cannot do a natural log of a minus number. You'll get an undefined answer. But with regards to the range here, you have a minus infinity up to a positive infinity, and you can see these are the domains here and this is the range over here. A good aspect about both of these is they are inverse of one another along their domains, such that if you have this line y equals x, you can show very clearly that both of these are one-to-one in terms of their correspondence, and a horizontal line would only cross these curves at only one point, and it would prove again that they are inverse functions of one another. A good characteristic of an inverse function, if a and b are inverse to one another, a good characteristic of both a and b is that because of their inverse relationship, their domains and ranges flip. Whatever is in the inverse of e to the x in terms of its domain and range, you'll have a flip. Because in the natural log, x is you will see very clearly right here, because the natural log and the e to the x function have an inverse relationship of one another. If you were to say this was f of x, the other one is inverse of that, look at their domain and look at their range. The inverse of exponential function is a natural log. And if this right here represents the domain of the exponential, the range of the natural log is equivalent to the domain of the exponential, and the range of the exponential is equivalent to the domain of the natural log. What does that mean in a very simplified sense? It means that for any function which has an inverse, the domains and the ranges, they flip. As you go from f of x to inverse of its function, what was the domain over here will become the range here. What was the range of this function will become the domain of that, and vice versa. You can see it the other way as well too. But in this video, we want to look at some interesting limit properties of the natural log function and e to the x, and we will do so. So let's look at the limit properties of this first. This curve, we want to look at everything over here with regards to three specific points: minus infinity, 0, and positive infinity. Exponential curve, this function right here is that curve in contrast to the natural log, where at all points, at any point where x approaches a either from the right or to the left, you can easily and clearly establish a limit. Why is that the case? Because at any point on this curve, if you look, which is a continuous curve, you can clearly establish right side and left side limits to be equal to one another. If you were to look at the point 0, limit as x approaches 0 for this specific function right here, you know you're looking here from the right side and here from the left side, and you see clearly your function e to the x arises at this specific value, e to the x, which happens to be e to the 0, which happens to be 1. And you find out that this specific function arises at a point called 1. And you can even use a calculator and use approximated values. From the right side you can look at 0.001, from the left side you can put minus 0.001 and put them right here in place of this x, and you'll easily come up with that value right over there. For the case as x approaches infinity, you're looking somewhere right here in the zone of infinity. You can easily look at values from the right, you can easily look at values from the left, though you don't have to, because conceptually infinity is too large a number that we cannot mentally grasp it very well. You could literally just put e to the power of infinity and roll with that, versus come up with approximations like what will you do as a close approximation to positive infinity from the right and the left. It will be again an extremely large number. You could easily say limit as x approaches infinity for this function, our answer or the function will approach infinity as well. Likewise, again, looking here in the zone of minus infinity, we're looking here at an increasingly large but negative number. You can clearly say e to the minus infinity. Either you're looking at it from the right side or from the left side, but you can always say that your function here will approach 0. Why would that be the case? Because you'd be looking at something like this. 1 over e to the infinity is a number 1 divided by an increasingly large number that it zeroes out. You don't even need to worry about, in these two instances here, looking at right side or left side approximations, because any approximation on the right of infinity or on the left of infinity, or however close it might be, is still conceptually too large of a number for us to fully appreciate in terms of a specific numerical value. So in all instances on this curve right here, at any point, whether you're looking at minus infinity, 0 or infinity, or any point in between, you can easily establish right side and you can easily establish left side values. So in all of these instances, as x approaches either a from the right or a from the left, what are these a values will be on your x-axis, what are these values will be, you'll easily come up with a satisfiable limit from both sides of that specific value, and your function will clearly have a specific value that it reaches. Now this natural log function is a special case when in contrast to the exponential function, in that you cannot easily on all instances on the curve establish right and left side limits, because there's a specific area on this curve where you can only look at it from a right side but not from a left side. For this specific function, if you were to look at these points 0, 1 and infinity, you can very well establish right side and left side limits to be equal over here, and of course any points in between, but not over here. We will first look at these two, then we'll look at this. If you're looking right here in the zone of infinity, limit as x approaches infinity, again you don't need to really look at right side and left side limits or approximations which are so close to this infinity on either side, because it would be conceptually difficult to do so. All you would really have to do is just look at something like this natural log infinity, and you could clearly say your limit for that specific function as x approaches infinity, either from the right or the left, would still equal infinity, and it would be right, and you would know why that is the case. When you're looking right here at 1, limit as x approaches 1, you could do so from the right and from the left and still arrive at the same answer. As you're looking over here from the right and from the left, your function will approach this value right here, which is 0, and you'll clearly have this value over here from both the right and the left side, and you can say that a limit for natural log x as x approaches 1 from the right and from the left, the limit does exist for this function, so it does exist. However, the case is not what it would seem as limit as x approaches 0, because this right here is only a one-sided limit. You don't have a left side limit, because you literally right here, my x equals 0 line, which is your y-axis, you have no values here approaching 0 from the left. You only have values approaching 0 from the right. We're looking at these values here on the curve along the x-axis. You don't have this aspect at all for the natural log function here. You only have, in this case, a right-sided limit as x approaches 0 from the right. Your natural log function goes towards minus infinity, because you're seeing it's going down here towards the realm of minus infinity. So you only end up having a one sided limit here for the natural log function, and even that as you approach 0 from the right. As limit as x approaches 0 from the left, you would have to say that the limit does not exist, or there is no limit over here, because you have no extent of this domain involved after 0, let alone 0, because you cannot do a natural log of 0, it's undefined. You cannot do a natural log of any negative number, and that's undefined as well. So in some instances you have to be a little flexible or remove the rigidity of the rule that a limit exists for a given function only when both the right side and the left side limits are the same. In all of these instances I've shown you the right side and the left side limits are the same, except for right here. For this function natural log x, as x approaches 0, you only have a single right-sided limit, no left-sided. Therefore you have to accept the fact that for this specific instance you have one-sided limit, and you have to roll with that for the natural log function it ends up being minus infinity. Now in the last part of this video we look at the differentiability of natural log x and e to the x. You know derivatives deals with a special kind of limit, and that's to do with the rate of change, or you can say the instantaneous rate of change of a given function at a specified point. And we also know that a function is differentiable if it is continuous, but more so you can clearly say that if a function has a derivative over a domain, let's just say a to b or minus a to a, if a function has a derivative that can be determined over a specified domain on its curve, then you know during that interval of that curve the function had to be continuous. But not necessarily that a function is continuous. You can see a derivative come out simply because of that continuity, because you can have issues such as kinks or corners that can affect the differentiability of a function, because at kinks and corners you cannot really determine a derivative. You can also have vertical tangent lines arise where you may not be able to determine a derivative of a function. You know, right here, here's a kink and a corner. It's a continuous function, but you can't do a derivative over there. In this curve right here, you have something which goes like this. You have a tangent line, vertical tangent line. It's continuous, but you can't do a derivative here. You cannot do a derivative over here. But natural log x and e to the x, the exponential function, are continuous. And over their continuous domain, you can easily do derivative determinations. Let's just look at this one, right? E to the x. You know it looks something like this. By now it should be like second hand to us. At any point on this continuous curve, you can easily determine a derivative. If e to the x represents your original function and you were to determine its derivative, we know the derivative by using the template technique, d over dx of e to the x is always equal to e to the x, or e to the ax is equal to a e to the ax. But we're right now looking at this very basic function over here. At any point over here, if you were to pick specific points based on the domain, at all of these points you can easily and clearly draw tangent lines. Each of these tangent lines will represent your instantaneous rate of change. If you were to map these out in terms of a plot, at this minus large value, whatever it might be, you have a slope of a tangent line, and you're basically now graphing. What are you graphing? You're graphing x-axis points against slopes of tangent lines. If you were to take these x-axis points, which represent areas where you were to determine the slopes of the tangent lines, and that's your y-axis values, look how your curve develops. At this value you have a relatively shallow but positive slope value, because here m or here would be a positive but it's a flat. Here m again is positive but it's still a flat. And here, as you're going across this curve now, the slope is still positive but it's becoming more and more steep. If you were to plot all of these points, these x-axis values with the relative value of these slopes, look what your curve would look like. You would have something like this which would pop up like this and would exactly mirror your this original function, which is why graphically you can say easily that the derivative of e to the x is just e to the x, because when you plot the points at which these instantaneous rate of change calculations are made, or the slopes of the tangent lines which are represented by the instantaneous rate of change, if you plot these two, you end up with this type of a graph. And this graph exactly mirrors what you started with. It's a little more interesting when you look at the natural log function. When you look again at this, f of x is equal to natural log x. If you do the derivative of natural log x, we're not talking about natural log ax, we're just talking about natural log x. You know your derivative factor or your rate of change is calculated by this expression over here. Natural log x becomes 1 over x. If you were again to do the same exercise where you take possible x values and then you plot them out against what the possible slopes of the tangent lines would be at those x values, you could actually see this curve come out from this natural log x. If you were to take this value over here, it could very well be just 1 over 2. At 1 over 2, you know how the curve is going. You have a pretty steep tangent line you can draw, and we'll just say a very steep, like a very steep tangent line. And then as you're going closer to this point right here, 1 comma 0, let's say here 3 over 4, right? You cannot go into the negative zone, you cannot go 0 because natural log of 0 does not exist. But 3 over 4, you can see now a tangent line drawn over here will be a little less steep, but it's still a positive slope. These are positive because these lines, tangent lines, were still pointing upwards from left to right. The line goes upward. This will be positive steep, but not as much. At this point right here, 1, you still can draw a good tangent line. It is still relatively steep, or you can just say its slope is like 1, equally flat, equally steep. And an arbitrary point, let's say 10 right over here, you have a relatively less steep. It's still positive, but it's kind of getting flat, but it's less so. And then if you were to come out over here like a 1000, you know your curve over here is still going to go towards positive infinity, but your lines will get very flat, and you can just say it'll be a positive slope, but it'll be flat. If you were to take these data points and graph them out, you'd get a good graph of a derivative of your original function natural log x, and let's plot them out. At 1 over 2 we have a very steep, and these y-axis values represent these slopes of tangent lines. At 3 over 4 we have still a steep, not too much. At 1 we have 1 over here. At 10, we're not going to draw this to scale by any means. At 10 it's positive, but it's less steep, generally more flat, and going all the way out to 1000 we have very flat, such that it's, as we approach infinity, the slope of the tangent lines will really be approaching 0, but you can see the curve comes out like this, and this happens to be the curve of 1 over x, a hyperbola. And you can clearly see over here, both of these functions, natural log x and e to the x, are easily differentiable along their entire domain, because they're continuous and there are no corners, there are no kinks, there's no vertical tangent lines arising, and you can easily see how graphically you can determine the derivatives of these two expressions using this procedure over here. It could be stated here that as this goes down here towards minus infinity, you may end up seeing vertical tangent lines, and then at those specific points on this domain you may not be able to calculate a derivative, but who's going to go down there anyways? And if you were to take this all the way up to positive infinity, eventually you could start seeing these arise, slopes of equal to 0 or very close to 0. That's all I wanted to present to you all in this video. I hope it's meaningful content over here. Thank you for watching. Have a nice day.